Hi again. So in this video, we're going to do our third full hypothesis test example. And this one has to do with body temperature. Okay, something you might be familiar with after taking your temperature a bunch for COVID and all that stuff. So, or just in general. The regular body temperature for healthy humans is said to be 98.6 degrees Fahrenheit. Is this really true? I've often wondered this myself. I don't know about you, if you usually get higher or lower than that. So is that the true value, or, was that, maybe it was never the true value, or maybe it was and it has changed? So a couple different questions here. Alan Shoemaker, need to capitalize that. Alan Shoemaker presented some data derived from a study of healthy adults, where the sample mean of 50 adults was 98.26 degrees Fahrenheit. Do these data provide significant evidence at a 5% level that the average body temperature is really different from the standard 98.6 degrees Fahrenheit? Okay, so Alan Shoemaker, I believe, is a statistics instructor who used a study that was made on this, but he sort of adapted it for a statistics class. Okay, so we have a sample mean of 50 adults, and this is our observed statistic, right? So the observed statistic is always coming from data or from a sample. So look for what would be our null then, and also what type of parameter is this. Okay, those are the things we want to look at first. So let's see, I've got 50 adults, so that's my N, right? And then it says sample mean right there, so that's X bar. Okay, so this tells me we're looking at means, right? Also, we have units, and this is a measurement. So this is our mu naught for our null distribution. And then this is our X bar, our sample statistic or observed statistic. Okay, and then we're testing, do these data provide significant evidence at a 5% level that the average body temperature is really different from the standard, what we've all been taught, 98.6 degrees. Okay, so this is not giving a direction one way or the other, it's saying different. And remember, this would be specified before we take data. So the fact that we don't want to let this fact that the sample mean is lower necessarily lead us to a left tail test, right? Because we would be setting up our hypotheses in advance of collecting data, okay? So let's write our hypotheses. So we have a mean this time. H naught, or H null, mu equals, so we have a mean, so it's mu equals 98.6 degrees Fahrenheit. That's the commonly accepted value, status quo, etc. You'll notice I took off the training wheels for this problem. I don't have the steps, but I have them nearby in case we need them. And then the alternate is mu again, and that's like a U with a tail. I haven't written mu a lot yet, so that is going to be greater or less than or not equal to, right? So this one is different, so I'm going to put this in green, is a not equal to. And then the null value, the value is the same in both. Just like with our proportions, the value is the same in both hypotheses. The only thing that changes is the 0 and the A and the symbol in between, right? Okay, so those are our hypotheses. What's next? Think about what the next step is. Okay, well, often we write out what our observed statistic is. So we might want to write our X bar is 98.26 degrees Fahrenheit. And because we usually need it for our randomization distribution, I'm going to write our N of 50. So we're going to be looking at a bunch of random samples of 50 adults. And how likely is it, if the null is true, how likely is it to get this low of a value? Is it likely or is it unlikely? Okay. I don't know. I can't wait to find out. So now we're doing means. So I'm going to go over to stat key and go to test for a single mean right here. Okay, now when you do means, it's a little different than a proportion. With a proportion, all you need is a p and an n, and you can generate a distribution. With means, you need like a data set to get to randomize from. So body temperature happens to be the default in this one, and then you might be asked to go to a different situation in one of your homework or test or quiz questions. Okay, so I'm going to stick with body temperature. I'll show you the data table. This is a sample, and it's a sample of 50. Now notice, let's just double check. We do have, yeah, so this is actually our X bar right here. This is our sample from the question. And you can see our mean. This is our X bar, 98.26, okay? Now we need to put in our null. You can see I was practicing this. 98.6. I had to generate it for the notes. 98.6. And then, let's see. That is all I need to enter for this one because our n is going to be fixed by our sample. Because we have one sample of 50, we're going to be generating a whole bunch of samples of 50. So I don't need to edit data in this case, okay? But if you, let's say you were given a set of data, then you could click edit data and then you could copy your data in right here. So that's another way, another thing that could happen. Okay, so here's our sample. So what we're going to do is go ahead and generate. I'll do a couple since it's our first time doing this. I'll do a few. Now remember when we generate, this is different. This is not bootstrapping from this sample. Because remember, we're assuming the null is true. So what they're having to do is generate a distribution that has our mean of 98.6. Okay, so it's the magic of technology. And you can see here's our null, the arrow at the bottom. And bottom in the center has a null of 98.6. That's where, that's our null value. And then you can see a randomization sample here. Okay. And I think they're using roughly the same standard deviation. That's the tricky part with these, is what standard deviation are they using? I think they're using the same as the sample. And you can tell it's roughly, it's close to this actual standard deviation of the original sample, but this is not resampling, okay? Here we're just getting a null distribution, the null world. Okay, doing a bunch, up to 30. I'll do a few more, up to 100. Do some hundreds. And we're seeing a familiar shape, right? Okay, that's up to 1,000. I'm going to generate another 1,000. Once you feel comfortable, you can just go right to 2,000 if you like. Okay, so this null value does look like it's right in the center of our normal shaped, roughly normally shaped distribution. Okay, so this is our null. This is assuming the null is true. This is what 2,000 random samples would look like, okay? So now we want to compare our sample and see how likely is that to occur. Now, is this a left tail, right tail, or two-tail test? Okay, if you said two-tail, I didn't write it down, so I'll write that down when we go back. If you said two-tail, you're right. I may have said it, I can't remember, but it's the not equal. So that means it could be off in either direction. Okay, so I click two-tail, and then let me make sure this is all visible. So we have our 95% in the middle, but we're interested, well, that's the default, right? It always comes up with the 95% in the middle and the 2.5% in the tails. We want to go down to our scale at the horizontal scale, and we're going to enter, this is the interesting thing about two-tail. We have to figure out which tail we're on. So our observed statistic, is it less than the null or greater than the null? And that determines which one we'll enter. We don't want to enter the wrong one on the wrong side. I haven't actually done that yet, so I'm not quite sure what would happen, but I don't think it's going to go well. Maybe I'll do a test and see what happens. So our X bar is 98.26. So that is on the lower side, right? And oh, it's way down the left of the distribution. So yeah, I'm curious to see how this works out. So I'm going to click on the left value down below on the horizontal axis. And I'm going to enter, you can see I've already done it, 98.26, enter. Okay, so wow. Notice how it adjusted the other tail to match. So it's using symmetry. If I figured out how far this was from the mean, it's going the same distance on the other tail. So we're using the idea this is a symmetric distribution. And then there's only one red X on each side. So it's only 2 out of 1,000. And you can see 0.999 is, it's 2 out of 2,000 or 1 out of 1,000 because we did 2,000 samples. Okay, so then our p-value, because it's a two-tail test, we're going to add both of these. These will be the same because of symmetry. So you can add them together or you can multiply by 2. Okay, so that is another feature of a two-tail test. Your p-value is twice as much. Okay, let's see. Is there anything else I want to show you before we go back to the notes? I don't think so. So let me write down, I want to go back up here and write in green, two-tail test, because it says different from. It's not giving us, it's not saying greater than or less than. Okay, so it could go in either direction. And then here I have by the magic of television, the magic of YouTube, I have a randomization dot plot right here. Now what's interesting is this time I actually got 0 p-value. None of them came out to 98.2. Why do I have 98.241? That could be my problem. This should be 98.26. I don't know, somehow the wrong number got in there. I don't know what happened. So let me write our results from what we just did. With 98.26, and then I'll go back to the notes in a second, but I got to look at the numbers here. The symmetric value is 98.941, and then in the middle we have 0.999, and for each tail we have a probability of 0.0005. Very tiny. 0.005, yeah. And each one is 0.0005. Okay, so let me go back here and show you. I changed all of that. Okay, so our p-value, we're going to add these together. Now, it is possible that just due to another random variation, you know, you could get a p-value of 0. So it is possible to get a p-value of 0. It looks like somehow I just got a typo in there. I thought that was a little unusual, but, you know, it does happen. So let's write out our p-value now. Our p-value equals, I'll show it both ways, 0.0005 plus 0.0005, or 2 times 0.0005. Okay, and I've located my calculator. 2 times 0.0005. I usually find it easier to multiply. It's just faster, fewer digits to type in. Equals 0.001. Okay, and I want to save room for my conclusion because I don't have my ABCDEs on here. So over to the right here, I'm going to write, I'm going to compare my p-value with alpha, okay? So I'm going to say our p-value equals 0.001. That is definitely less than 0.05, right? So this is significant. Okay, I'll save writing the word statistically for the conclusion instead of writing it twice. Okay, so I didn't check though. Yes, okay, fortunately I didn't check because if we had a different significant level, but they did give us the 5% significance level, so good. Very good. Okay, and remember, even though it looks like I had a typo here, we would also get variation with this too. So yours might come out a little differently. It could be 0.00002 or 0.015 or anything around the same. But this is very clear that it's significant, right? It's not like it's 0.49 and 0.51 or 0.49 and 0.51. Okay, so I'm going to say with a p-value of 0.001, the result is statistically significant. Okay, so now I'm going to talk about, do we reject the null or do we fail to reject the null? So remember, statistically significant means there's evidence for the claim. So we reject the null. Reject the null hypothesis. There is evidence. Or you could say significant evidence that the body temperature, let's say human body temperature, is different than 98.6 degrees Fahrenheit. So it seems like it's lower, right? At least with this sample, and I've noticed mine usually comes out lower as well, almost all the time. I just didn't know if it was the thermometer or something weird about me, who knows. So curious what you all have experienced, if you found that your body temperature is usually lower than 98.6. Okay, so another significant result, this time a two-tail. So I do want to make one note about two-tail and multiplying the p-value by 2. So let's put that up by the two-tail, where I wrote two-tail test. Of course, you can write it wherever you like. Two-tail test, so we're going to have I'm going to say add the p-value in each tail, or multiply one tail by 2. Okay, so you might be thinking like, well, that really kind of changes your significance level, right? Because if you're multiplying your p-value by 2, you're doubling it. So it really has to be half as significant. So you're right. It is to an advantage to your advantage to specify a direction early on, but if you don't know, you don't know. So, okay, there's one more thing I wanted to try, and that was what happens if I put, just an experiment here, because it could happen. What happens if I put the 98.26 in the wrong tail? I'm going to see what it's going to do. How smart is this? Okay, yeah. So if you end up with a lot of red, you put it in the wrong tail, because I put the 98.26 is below the mean, but I put it in the one above the mean, and it's just very confused. It's now everything is above that, so it's all red, and it's like 0 in the middle and half in each tail. So if you end up with a thing all red, just double check. You put it in the wrong tail, okay? Does that make sense? So let me go back and fix it. I don't remember what that was though. So I'm gonna uncheck two-tail, so I can do that to reset it. So if you uncheck two-tail, that'll reset it. Check two-tail again, and it'll bring up your two values along the horizontal axis. And then I'm gonna put it in the lower one, 98.26. Enter. And then see, we're always going towards the tails, right? We're concerned about the extreme values that are unlikely to happen. So we're always going towards the tails. So the red should only be in the tails. The tails can be bigger or smaller, as we've seen. These tails are very small versus the flat tire. There was more red in that one. So just a little tip in case you put it in the wrong side, and just switch it around to the other side. Okay, great. Thanks for watching, and I'll see you in the next video.